where we moved on to function approximation, and last time we introduced, might have taken too long doing it, but introduced the notion of linear functions, which is a nice starting point for function approximation. And here we just define some features of the state, and we're learning a value function, and we assign weights to those features, which give you the importance. And last time we looked at some examples where, well, we said here you're able to represent the value function using the features. And then we gave another example where we changed things a little bit and the same features were not adequate. And, this is just a concrete example of how defining these features is not always straightforward. Usually it's an iterative process. You'll come up with some features, you'll try to learn, and you'll see the agent doing something weird, and you'll say, hey, maybe it's doing something weird because it doesn't know this aspect of the environment, and you'll add a feature in. So it's usually iterative, but that is a very well-known approach. So now the question is, how do we actually learn these value functions? So previously, we learned a value for every state, sort of explicitly. Now, the only thing that we have to adjust is these parameter values, theta, right? And there are many fewer parameter values than there are states, and that's why we're hoping to get some savings. And so we're going to use, to begin with, the same type of RL loop that we've been seeing before. So you will go around, you have an explore-exploit policy, you take an action, you'll update a model if you actually are only learning a value function. And then the different part here is that we'll have to adjust the parameter as opposed to adjusting V of S, for example. And that's the new thing that we need to talk about now. So how do we update a parameter? Somehow we'd like to update it in a way that's going to make the function sort of, remember, all of these loops, all of these updates were sort of the form, here's a target value, right, that we use Monte Carlo or temporal difference learning to say, here's a target value, and we want you to move the learned function in the direction of the target. Right? That's what all of our methods were doing so far. And we want to do the same thing here. So if we have a target value, how can we move the parameter in a way that moves the overall function in the direction of the target? And so some of you who have taken machine learning and deep learning will have seen this sort of thing before, but we're going to review it anyway, for even if you have seen it and for those who haven't seen it. So the typical way to do this is with something called gradient descent. And so the idea here is you have some function, I'm going to call it E, for error. We're going to think of this as an error function. And the function's a function of some number of parameters, n, and we'll think of these as our weights, our weight parameters. And I'm just showing you a couple of ways of, if you were to plot this function and there's only two parameters, what it could look like. So you could have a function that has many local optima, lots of hills and valleys, or you could have a nice convex function like this that's really nice to deal with. But in either case, what we're going to want to do is to find parameter values that minimize these functions. So we're going to think of this function as an error function. So we want to have small error. Okay? And so the typical way of doing this is gradient descent, which is nothing more than you start out at one point on these functions. And then you're going to find the direction of steepest descent. That's just the gradient. Then you're going to move in that direction by some amount. Then you're at a new location, and you do the same thing over and over and over. Okay? So you're going to do that until you reach some place where you kind of get stuck and you can't decrease anymore. So basically moving downhill. And as I said, the common way of doing this is with gradient descent. So a lot of these words are, you can read them on your own at home, but using vector calculus, if you have a functional form for the error term in this case, and we'll show what this might look like, you can take the gradient, and that gives you a vector, which, if you remember from vector calculus, is basically just, you look at the derivative in each direction independently. And the overall gradient of steepest descent is just independent steepest descents in each dimension. Right? So the gradient is a vector, which is the same dimension as the space that you're searching in, and it tells you where to move. All right? So you can decrease the function by moving in the negative direction of the gradient. So are there any questions about this? Probably a lot of you have seen gradient descent before. So how does this apply to us? Well, suppose that some oracle gave you a sequence of states paired with the values for those states, right? So that would be really nice if somebody would do that to us, right? Here's a sequence of states and the values for those states, and I want you to learn the value function from this data. Right? This would be more like a supervised learning problem, a regression problem. But we're gonna start thinking about this, and then we'll replace these oracle values with our target values that are estimated in the RL loop. Okay, so if you're given this sequence, we're going to define our error function for any individual element of that sequence as the mean squared error. Right? So this is our current value function estimate. Right? We have some current parameters, and for any state, Sj here, it's going to give us a value that we think is the value of Sj. And here's the target value. And so this is just how far away are we from that target value, and the 1/2 is just to make the math work out nicely later. But this is mean squared error, or the squared error of this one example, and it's a very common thing a common way to measure error for regression problems. And what we can do is, after we see this example, we could do sort of what we're going to call stochastic gradient descent, which is move the parameters in a direction that make this smaller. Right? We could do that by just computing the gradient of this and moving in the negative direction. So we've kind of put and this is a learning rate. Right? So you're always going to have a learning rate, and these learning rates are one of the things that really influences how well these train, and we'll talk about different ways of setting that later. A lot of neural net libraries have a whole bunch of optimizers that give you various ways of changing learning rates, and people have their favorite ones. But this is what we're going to do, and so you would do this for each dimension independently. And so if we look at, just go through the details here. So what's the gradient of what's the gradient of EJ with respect to this parameter, theta I? Well, we're going to use the chain rule to rewrite that. So it's EJ with respect to the value function estimate, and then the value function estimate with respect to this. So basically, how does the error change when our value function estimate changes? Then how does the value function estimate change when our parameter changes? Right? This is just the chain rule. And we can look at this. Well, this is just, you look at this expression here and you get just this, right? That's the partial derivative there. And then this depends on the functional form of v, right? Because the neural network is going to be something, if it's a linear function, it's going to be nice and simple. So for a linear function, the gradient of this with respect to theta I is just going to be the feature fi, right? The value of that feature. Because the rest of these are all sort of treated as constants, with respect to theta I. So is this fine so far? Right. So we're just doing basic calculus. And so the update becomes this for the parameter ij, for parameter theta I. And this makes intuitive sense. So if your target, for example, is larger than your current prediction, right? This is going to be positive. And if the feature that you're considering now for the theta I happens to be positive, then you want to increase the weight, right? You want to make the linear function more positive. And so this is going to increase the weight. If you're overestimating, if V, your target, is larger than your current prediction, this will be positive. And let's say your feature is negative, well, you're going to decrease the weight, because if the feature is negative, you want to make the function less negative. So the signs make sense here. It's always good to do a double check, because half the time you'll mess up the sign. So this update, if you keep on doing it over and over and over, and the data that's coming in is from a consistent linear function, this will converge to the best fit, the least squares solution. So you have to have the right learning rate schedule, but that's all theory. A lot of times if it's just a linear function, you'll pick just a small learning rate, and you might anneal it over time. These are the art of training these things. But at the end of the day, that's what you have for an update. So if you just go with that, you could say, well, here's my RL loop. I've got an RL loop. I end up in a state, and the thing that's not specified is what the target value is, right? So do you have any suggestions for what that target value should be? What would be one? Right, we're running our policy, and what have we used before for target values? Yeah, so you could do a TD approach, would use the current value function to get a target. I guess another one would be, this isn't as common, you could do Monte Carlo, right? So you say, well, this would require that you have run a full trajectory, right? So if you've run a full trajectory, when you're at state ST in the trajectory, you can say, well, this is going to be the target value, the future value that I observed, and you would plug that in there and do an update. It's just, you have to adjust the code so that you wait till you have the whole trajectory, and that's kind of annoying, but you could do it. So that's the MC approach, but you could also just do this, the TD approach. So the TD approach will say, well, I observed this reward, and then I got to my next state S prime, and this is my current estimate at S prime, and so this is R plus the discount factor plus the next state estimate. So this is just like what we did previously, except previously we had a table that was storing these value estimates. Now we have this linear function storing the value estimates. So just a little bit different. And so if you go through all that, this would be a basic algorithm that will do reinforcement learning with linear function approximation. So it's pretty straightforward. The same loop. It's just now you're adjusting each of these theta i's instead of adjusting the particular state value. So any questions about this? Right, and of course we have to learn the model, because to take the greedy action, we only have the value function right now, and so we have to have the model to do the greedy action. We've talked about that before. Yeah, and we'll see an example in a moment in backgammon where you already have the model, and they actually just used this basic algorithm to get a world championship player in backgammon. They used a neural network, but the same idea was there. All right, so okay with this? Right, you could all implement this relatively easily. In fact, you take the homework that you're going to be doing for the table-based methods. Well, we'll have a Q learning version of this in a moment, and you could very easily adjust that to be something that learns linear functions. All right, so we know that a lot of times we're not going to want to mess around with a model, like having to learn a model and use it for one-step look ahead. And so as we said before, we use Q functions when this is the case. So I give you the Q function, you can just maximize the action, and you don't need a model. And so for function approximation, this means that you're going to have to represent the Q function as a linear, well, for the linear function case, as a linear combination of features. All right? And it seems like the features are going to have to depend on the actions in this case. So why do we need the features to depend on the actions? Why can't we just have features that are functions of the state? Right? So why not just have f1 to be a function of the state? I've got them all depending on the action somehow. Not a trick question.
Q values are different for different actions.
Yeah. So if the feature is only dependent on the state, this is going to be a constant for every action. Right? So it's kind of it's an obvious thing, but you just need to remember that because this can complicate defining the features. Right? The features now have to be a function of the states and the actions, which sometimes is straightforward, sometimes not. I'm going to show you a trick in a little while, in a little bit, that if it's not straightforward, it gives you something that you can do if you have features on states and not actions. So I'll also show you an example where we're doing state action features is also relatively natural. So we'll look at some examples in a moment. But just like for TD, you can easily extend it to the Q function. And we had two ways of doing that. Like one started with generalized policy iteration and you got SARSA. The other one started with value iteration and you got Q learning. And I mean, this is why I told you at the beginning of the class, if you learn the basics, like the table-based stuff, like this is just all, plugging in one little line that's different than before. So you're doing, high-powered machine learning now all of a sudden. But you really haven't learned anything terribly new beyond what we've already done. You've just learned how to update parameters, but everything else is the same. So SARSA will be exactly as we had before. The target value for SARSA, remember, is the reward plus the Q function evaluated the action that was taken by the policy, like the action that was actually taken in S prime. Right? So this is the SARSA algorithm. But there's really nothing to change other than this line. And technically there should be a loop over all the i's. I didn't show that, but you would be updating all of the i's here. Q learning. Right, there you go. You've got Q learning for linear functions now. The only difference between that and SARSA is that we do the max over the actions. Right, that's how we do Q learning. And so you can get Q learning with linear function approximation. So the real question is, are there any sort of guarantees with this at all? Right? Is it, we guaranteed it's going to return. So do you think we could have a guarantee that it will always converge to an optimal Q function? No? Yeah. Why not? Any reason why not?
That local minimums.
Okay. Yeah, maybe. But maybe for a linear function, maybe this does converge somehow. Right? But maybe mathematically it won't. We haven't got that far. But is there something more fundamental?
What guarantees your representation is good for your problem?
Right. So we've picked some features, and if my features are inadequate for the problem, they don't capture what's necessary to capture the true optimal Q function, there's no possible way that you can learn the Q function using these features. So your features have to be good enough, and you're really, once you go to function approximation, you're never really thinking about learning optimal things. I mean, you hope, but you're trying to get Q functions that end up giving you good enough performance. And you really never know if you're close to optimal or not. That's just a fact of life once you move to function approximation. So yeah, the linear function could be inadequate, and then it could be really bad, right? And then you're not going to be able to converge to anything good. It would be nice if you could say, we're going to converge to like the best Q function in our space, something like that, or the Q function that is closest in mean squared error sense to the true optimal Q function, right? So it'd be nice if you could say something like, we're going to converge to something that's as good as we could possibly do, right, with the representation we have, because you can't ask for anything more than that. Unfortunately, you can't really even say that. The convergence of these things is pretty wacky and not very well characterized. Yet we use them, and it gets even worse for neural nets. Like you basically know nothing there. Yet you use them. These are kind of engineering tools, and because you have no guarantees, you also have to kind of be careful if you're putting this thing in a situation where you don't want it to screw up. So there's a lot of testing that you would have to do. But let's see what they say about convergence. I've never studied these things in detail, but your book talks about a couple of situations. So SARSA, since it's on policy, I'm going to show you an example in a moment that shows Q learning breaking very badly. The on policy nature of SARSA lets you get some convergence results are a little bit stronger than Q learning. So they can say that it converges to a region, like some fixed region, but the quality of that region is not very well characterized. It's like the quality guarantees they have on the region are so loose, it's like, it's not even really that meaningful. So, but they can at least say it doesn't diverge. So that's something, right? Your Q function is not going to blow up. So not terribly satisfying, but that's what you have there. Q learning, on the other hand, you can blow up. So if you're not careful, and I've seen this happen before, and we'll see when we start talking about deep reinforcement learning methods, there are mechanisms that people employ to try to prevent this, but this can happen. So Q learning with linear function approximation can cause you to blow up. And one intuition about this, and this is if you start implementing this, sometimes you might come across it. So Q learning, you could say, is a little bit dangerous in this setting because in the beginning of learning, this Q estimate is going to be pretty bad, right? And what if it's bad in in a way that makes it quite large, right? So this is maximizing over all the actions. And so at some level, if you're if your error is sort of your function is too large, this is like returning the worst possible sort of error point of your function. So what can happen sometimes is this is where the self referential learning can really go wrong. So we take an action, we end up in state S prime, and then we ask ourselves, well, what action has the highest Q function? And if our internal understanding is bad, like this could return something that's really large, right? Because we've never been in this state before, we've never taken any actions before here, yet this is somehow generalizing from our previous experience now, and it might return something that's really large. And that will cause this thing to sort of give you a really large value, and it's sort of self fulfilling after that, right? You had a bad estimate in the beginning, uh, you update things, and that makes one parameter really large, and that can influence other parts of the state space, right? We're not just influencing now a single state action pair. When you make a change to the parameters, it influences everything. And so that could make everything blow up in a sense. So the max here can cause some problems, but it's not even just the max. It's really the off-policy nature, which this example, this is sort of a classic example of Q-learning blowing up that we can look at now. So just imagine that this is part of an MDP somewhere, and let's just say it's an MDP that has one action. So this is a trivial problem, and yet we're going to show that Q-learning blows up still with linear function approximation. So we have two states here that we're going to focus on, and one action, A0, and the feature value for this state and this action is 1, and the feature value for this state and this action is 2. Right? So that just happens to be what the features were. And we're going to represent our Q function in this way. It's just going to be one parameter times the feature. Right? So you're just scaling that feature value. So looks like a pretty benign situation. Zero reward, right? So if this was all you had in the MDP, you'd have to have some self transitions here. The value of this would just be 0 or something. And you can put this in an MDP, but just for illustrations, all you need to do is have this transition to show the problem. So now let's consider a single transition where we transition from S0 to S1. And we're going to do a Q-learning update on that. Right? So let's see what that update would look like. So the parameter, if we went back and looked at our equations, we're going to have the parameter, then we'll have alpha, our learning rate, then it's the reward, which was 0, plus our current estimate, and we're not going to, we'll plug that in a moment. And then this was also our current estimate at S0, then our feature value at S0, which this was 1. This had a value of 1. So we end up with this. You can go through the math, but at the end we end up with this expression here. And so if we look at this, what can we say about this expression? Like if you consider different, let's think of alpha as just being a fixed value, less than 1, greater than 0. Beta is our learning rate. What can we say about this? Is it ever greater than 1? Yep. So alpha will just take to be kind of a constant. Yeah, so when beta is greater than 0.5, right, this is going to be positive, and this will be greater than 1, right? And if this is greater than 1, it's going to cause theta to get larger, right, by a multiplicative factor, right? So this seems to be a problem, right, because we didn't say anything about what the value of theta was. So if you do this transition once, theta is going to get bigger by a multiplicative factor. If you do that transition again, theta is going to get bigger again by a multiplicative factor. And this will just blow up. It's just going to keep blowing up. Right? So every time you do an update here, theta is going to get larger. Even though it shouldn't, right? You could create an MDP here where the right value is 0. Right? This is a reward of 0. So that's fairly disturbing, right? So this is just showing you an example where Q-learning can really cause some problems. Right? So does this example make sense? Right? It mathematically, this is sort of the classic example that you'll see in textbooks, and SARSA doesn't fall into this problem because it's an on-policy algorithm. So it would also have to be updating it would also be forced to sort of update S1 based on the action that S1 takes. And it's a little too detailed to get into, but that causes things to stabilize a little bit. So you at least don't blow up. But Q-learning, you can't make any assumptions about what transitions you're going to be updating on because it's off policy, and you could update this transition as much as you want, and things get bad. All right. So that's just kind of a fact of life with these algorithms. There's not many guarantees. You can say Q-learning has poorer guarantees, but that's it's not really necessarily a reason to prefer SARSA over it. But you have to be aware because you have to guard against these things sometimes. So I said we'd come back and talk about features a little bit more because we have to have these state action features. So sometimes, and I'll show you an example in a moment, it's natural to define state action features. In other cases, it's not so natural to define state action features, but it's easy to define features on the state. So in a game of chess, it's easy to define features on the state. Maybe not so easy to define features that are a function of the state and action. Maybe you could think about that. But there will be situations where it's just it doesn't feel natural. And there's sort of a generic way to use these state features, a pretty simple way to get a Q function over states and actions. So what you can do, it's kind of a no-brainer. You basically just define an individual Q function for each action. Right? So this function here is going to be for the action AK. And for any state, it's going to return the Q function for action AK. Right? And so every action has its own set of parameters. Right? So the Q value for AK is going to be given by this. And then the overall Q function is just, you look at the action and you index the right Q function. Right? So this is a pretty useful, this is often what is done. And it's kind of obvious, but a pretty useful thing to know if you are trying to design these things. Right, so any questions about this? All right. So thought it would be interesting to show you a little case study of this. This is quite a while back now that we were working on this, but it's a nice little example of Q-learning in sort of an application context to a game, pretty simple game. But so what we're seeing here is, nowadays you might think of StarCraft, but back then we were dealing with this real-time strategy engine called Wargus, which was a open source clone of Warcraft. And this is showing you what we want to do is try to control our units to attack other units. And we want to win. And so this is sort of, you could think of it as multi-agent control. And we'd like to get a policy that can control any number of our units to attack any number of their units. So that seems like it's not so straightforward because you have to be able to generalize across these numbers somehow. And so let's see how we might try to do this using Q-learning and linear function approximation. Right? So what we're going to do is we're going to the states contain all the information about the units. Like what are their positions? What's the health of the units? What else is there here? More or less, it's mostly location and health, and what they're doing, like who they're attacking. Are they just walking? Whatever. Now the actions, the way we're going to structure the action space is you can send a friendly unit to attack an enemy unit. Okay, so if you take that action, it's going to send a friendly to attack an enemy, and it goes into like a Terminator mode. So if it's not close to the enemy, it will just start pursuing it, and when it gets close enough, it will start hacking at it. These are melee units, so they have to be close to attack. And the way we're going to do the policy is we're going to represent this Q function. So the Q function is a function of the state and the action. And each decision cycle, this is, you could say this is kind of a hack, but it's a pretty common way to do things. We're going to loop through each of our friendly agents and select an enemy for them to attack. That maximizes this Q function, right? And I'm not going over some details here because technically the order that you consider your friendly units is going to influence things. And when we consider a friendly unit and it makes its choice, we're going to update the state so that later units that are making choices know what the choices of previous units are. We call these pseudo-independent policies. So you can think of it as, I've got, this line of folks that are going to make decisions. He makes a decision and he makes it known to all of them. She makes a decision with that knowledge. She makes it known to all of them, and then we go down the line. All right? So it's a reasonable architecture. It is dependent on the order, though. You could get different actions depending on how you order the agents. We didn't have any particular, I think we just used the canonical ordering in the game. So now we can think about what, so our Q function is going to be a linear function, and we need to come up with features of a state and an action of this form, right? So we need features that sort of try to capture what is important about the state and an action that's involving some friendly unit attacking some enemy unit. And I've written down a bunch of the features that I think we used. So it would be, for example, one of the features might be the number of other friendly units on our side that are currently attacking the enemy. So why might that be a useful feature to know about, do you think?
It might be better to have more friendly units focus on an enemy unit rather than splitting them all one on one.
Yeah, that's one side of it. Yeah. Any other thoughts?
If you have enough to overwhelm the given unit that you're attacking and then some, then it's just redundant to attack them with more.
Right. So you want so basically you need to take into account who's already deciding to attack something, because if everybody decides to attack one unit, it's kind of a waste, right? They don't even have room to surround the unit. So you want to figure, this lets you trade off sort of how much you're focusing fire on individual units. So we also have the health of a friendly unit, the health of an enemy unit. Those are obviously the difference in health values. You can give that as a hint. And then the walking distance, right? That's pretty natural, because if something's way off, maybe it's not worth worrying about attacking that. This is an interesting one. This is one of these features that it doesn't make the first cut, but then once you see the policy that's learned, you're like, oh yeah, it needs to know that. So is the enemy, is that the enemy agent that F is currently attacking? So why is that maybe a useful feature to have?
If the if an enemy or but creature is targeting your given enemy, and it's just looking at the entire board, if it sees that on the opposite end of the map there's another enemy that's, say, near death or suddenly isn't being attacked by allies, it would not make sense to stop attacking this thing and just start jogging over there necessarily. But it might make that decision if it doesn't take into consideration what it's doing right now.
Yeah, roughly. Yeah. Any other thoughts on this? So I mean, and what you see, more like what you see if you implement this, is there'll be like, okay, an agent here and an agent here, an enemy here and an enemy here, and then the agent will just kind of go back and forth. And that's a really bad thing to do. Like you lose a lot of time, so you kind of want to focus on one thing at a time. And when you first create these features, you don't even think about that. And then you're like, oh yeah, it needs to remember who it's attacking because our agents didn't have any internal memory in this case, right? So yeah, so that's an example of we had to throw that in after we saw it fail and try to diagnose what's going on. And then yeah, is it the closest and whatever. So I forget how many features we had. We probably had 15, 20 features. Um, but the interesting thing, this framework is well defined for any number of enemies and friendlies. So that's kind of cool. You can just apply it to, if you learned on 5 versus 5, maybe it's not going to be great for 15 versus 15, but maybe it will do something non-trivial. We'll look at that. All right, so, well, this does get a little bloody, not by today's standards, but so these are our agents. This is the inbuilt AI, which is not very good. It's just some stupid. They have their own weightings of what to do, and our agents are acting randomly now. If you watch them, you'll see them like going back and forth. It's pretty. Yeah, it doesn't make a lot of sense. They'll whack and then they'll walk around. They're not doing too bad there. There you go. He's walking around there. But needless to say, they're going to get beat pretty badly. So the red was us. So that's where you start out. Right? So not too good. So that was this point right here, right? And I think I forget the reward function we had. I think it's just like a differential of hit points, more or less. So you get every unit starts off with hit points, and when you remove hit points for the opponent, you get plus, and when you get hit points removed, you get a minus. And so if you're in the negative, that means you've lost. Now, after just a little bit of learning, though, you start to do quite a bit better, and then it kind of stabilizes. And so this is going to show you. This is after only 120 battles. I mean, this is not that hard of a problem. And partly it's because they kind of learn to exploit the inbuilt AI, which is it has a proximity. So if you don't get too close to an agent, one of the enemy agents, it doesn't kick in and attack you. So they kind of learn not to get too close to the enemy. And that last guy eventually comes over. And so it's a nice little illustration of how just some basic Q learning can work pretty well. So this is a reasonably easy problem because you get pretty direct feedback. Like every time you hit, you get some reward. But yeah, so now you can say, well, what if we took that 5x5 policy and applied it to 10x10, right? So we'll see this. Try to run this thing. Come on. I don't know if it's running or not. Run. Oh, there we go. Okay, there we go. So you can see this is a bigger map. These guys are coming down, and they're not gonna. They make some pretty obvious mistakes here. They've never really played 10x10 before, but they still win. They still have this more or less this concept of don't get too close to things unless you have to. And so they wipe out those two, and they'll continue. But it's quite a bit different, right? Because they've learned on just 5x5, and so even the count values that they're seeing are very different than what they've seen before. Like you could have 5 people, you could have 6 people attacking one unit, right? And they do win here, but not by as much as they could. Yeah, but by quite a bit. So that was there, and I think we're almost done. Yeah, so pretty much they destroyed them, and then so that's where we were here. that's before we start. And then if you continue training on 10 by 10, you can improve even more. So and these are kind of random 10 by 10 games that you're training on. So, and each point here is sort of an average of, I don't know how many games you did. So that gives you a little illustration. So I guess we're done for today. Next time we're going to introduce deep learning, basically, and this is going to be deep learning, this slide. You replace F with Q of theta. So, all right, so we'll see you on Monday.